righty. So today I'm going to talk about nuclear radiation, basically what it is, how dangerous it is, how we can prevent it, the instruments that we use to measure it, and then the last thing is how is it beneficial for us. Okay, so Becquerel, which is a scientist, he did an experiment on nuclear radiation from a uranium compound. He found that it penetrated a light-proof covering of film. And he discovered in his experiment that different types of radiation have different abilities to penetrate. So the types of radiation that we're going to look at are alpha particles, beta particles, and gamma rays. Okay, so the three types of radiation and their penetrative abilities, alpha, beta, and gamma rays. Alpha particles can only travel a few centimeters in the air because they're so large. They have a charge and they are pretty massive compared to the other radioactive particles. So they have a very low penetrating ability. They cannot penetrate through the skin, but if they get inside the body through inhalation or ingesting it, meaning like you eat or drink it, it can cause damage inside of the body. Beta particles, which remember are basically electrons that are emitted from the nucleus, travel at close to the speed of light. Their penetrating ability is 100 times greater than the alpha particles, so they can travel a few meters in the air rather than just a couple of centimeters. And finally, gamma rays have the highest penetrating ability. They have the highest frequency, therefore they're the highest energy, and then they can penetrate through pretty much everything except for lead or thick concrete. You can see from the picture that alpha particles can't even get through a piece of paper. Beta particles can get through paper, but lead or glass stops them, but gamma gets through both of those, and then only through thick lead or concrete are you protected from gamma rays. Nuclear radiation can transfer energy from nuclear decay to electrons of atoms or molecules and cause ionization. That's basically, it can ionize the molecules in your body. So the Röntgen is a unit that is used to measure nuclear radiation exposure. And that is equal to the amount of gamma and X-ray radiation that produces 2 times 10 to the power 9 ion pairs when it passes through a cubic centimeter of dry air, just to give you an idea of what quantity the unit represents. Ionization damages living tissue. Radiation damage to human tissue is measured in REMS, which stands for Röntgen equivalent man, REM. So the REM is the unit to measure the dose of any type of ionizing radiation that factors in the effect that the radiation has on human tissue. So it's made specifically in reference to what kind of damage it could do to our bodies. Long-term exposure can cause DNA mutations that result in cancer or other genetic defects. So this is why I know there's probably like a meme or something out there, I've seen it before, about, or a joke, whatever, but X-ray technicians, and I think it's maybe a common joke that comedians tell about how, you know, if X-rays were okay for us to be exposed to, then why does the X-ray technician like run out of the room and like, you know, into a different room behind like a closed door? And the easy explanation to that is like, you are getting one X-ray, but that person is exposed to X-rays every single day as part of their job. And so they need to have a better protection. That's why they go into a different room. It's also the reason why when you get an X-ray taken, depending on the part of your body that you're getting the X-ray, sometimes you have a lead apron that they put on you to protect your vital organs just because of that fact. So DNA can be mutated through direct radiation, or even if it comes into contact with ionized molecules. So you don't even have to be exposed to the radiation directly, just with ionized molecules. I was just watching a video on nuclear fallout. And so I mentioned Chernobyl yesterday. And so when that nuclear core exploded, they had fallout, which basically looks like kind of like ash, I guess. It's like falling out of the sky, except for it's like heavily ionized. And so exposure to that also can damage DNA. Now, everyone is exposed to environmental background radiation. The average for people in the US, which I guess can be used as a standard, is about 0.1 rem per year. And the maximum allowed dose for safety is 0.5 rem per year. Airline crews and other people that work at high altitudes have increased levels because of two things. One, the increase in cosmic ray levels at high altitudes, but also because the atmosphere is thinner, and so they don't get as much protection. Radon-222 is sometimes trapped inside of homes. It's what do you call that? It's an isotope that leaks out through the ground. And sometimes people, you don't really see it here because in Thailand, I don't think any house in Thailand has a basement. But generally, in countries that have basements where you actually dig into the ground to form your foundation for your house, like underground, if they have cracks in the foundation, sometimes they can get radon poisoning. Right. So I just said that. So the problem with this situation is that there's no way to detect, well, I mean, there's no way to detect it, but it's not like it releases a smell, or it's not like smoke or something which would alert you that something is leaking out of the ground. It's really just kind of invisible, not really kind of, it really is literally invisible. So you could be, not here, obviously, but in places where they have basements, like I said, people sometimes are living in their house for many years and they develop cancer or other defects, and then they realize that they have radon leaking into their house. Hold on a second. You guys cannot hear that, correct?
Yes, cannot hear.
Yes, cannot hear. Okay. Test that. All right, so here we go. Okay, so basically what you just saw, he is at Chernobyl, and this is at the, was it Pripyat or something like that hospital? This is the hospital. Oh, sorry about that. Okay, so he's at the hospital in the Ukraine, which was used to treat the firemen and the technicians and people that worked in the Chernobyl nuclear plant. And what you see there is the, what do you call it? The, like the gear that the firefighters put on, that's still there. This is back from the 80s, and how much radiation it's still giving off.
Radiation is frightening. At least certain types of it are. I mean, my Geiger counter doesn't go off near my mobile phone or the Wi-Fi router or my microwave. That's because a Geiger counter only measures ionizing radiation. That is, radiation with enough energy to rip electrons off atoms. And it's measured in units called sieverts. If you're exposed to more than 2 sieverts all at once, you'll probably die shortly after that. But we're exposed to low levels of ionizing radiation all the time. Bananas, for example, are rich in potassium, and some of that potassium is naturally radioactive. So when you eat a banana, you're actually exposed to about 0.1 microsieverts of radiation. That's 1/10 millionth of a sievert. Let's use a banana for scale of radiation doses. You know, since people eat bananas, we become radioactive too. So you're actually exposed to more radiation if you sleep next to someone than if you sleep alone. But I wouldn't worry about that, because that dose is insignificant compared to the natural background radiation of Earth. I mean, there's ionizing radiation coming out of the soil and the rocks and the air and even from space. The level of radiation here in Sydney is about 0.15 microsieverts per hour. And that's about average globally. The level's usually between 0.1 and 0.2 microsieverts per hour. But there are places with significantly higher levels. So who on Earth do you think receives the maximum dose of ionizing radiation? Let's answer that question by going to the most radioactive places on Earth. Some places you'd expect to have high levels of radiation might surprise you. I'm in Hiroshima, and that is the Peace Dome. It was about 600 meters above that dome where the world's first nuclear bomb was detonated over a city. It was detonated there to have maximum destructive impact. But the level of radiation today, almost 70 years later, is only 0.3 microsieverts per hour. I'm about to get into an elevator. We're going down the mine shaft. This is an old uranium mine. This is the mine where uranium was discovered. It's also the place where Marie Curie obtained her raw material. 1.7 microsieverts per hour. It's about 10 times the natural background that you would have. Nowadays, most of the uranium has been removed. But in this wall, there's still a small piece, and you can see under UV light, it fluoresces. Look at that. Fluorescent uranium ore. This is the lab of Marie Curie. She won 2 Nobel Prizes, one in physics and one in chemistry. And she conducted a lot of her work here. And this is her office. She would have sat right there. Apparently, there are only a few parts of this area which are still radioactive. One is this doorknob.
Well, it climbs not much,
But that's like 10 times the background.
yes, more than 10.
And another is the back of her chair. You can still detect alpha particles coming off this spot right here. Apparently, after she was working in the lab, she would come, open the door, leaving traces of radium here, and then go and pull out her chair. Welcome to New Mexico. This is the Trinity bomb test site where the world's first nuclear bomb was set off. Right here, right in this spot. This whole area was vaporized. In fact, there was so much heat liberated by that bomb that it fused all of the desert sand into this green glass. And you can still find it here. They've actually named this mineral after the test. It's called trinitite. Yeah, this is the only place on Earth that this has ever been made. The level of radiation here is about 0.8 microsieverts an hour. The trinitite itself is a little bit more radioactive. I've got readings of 2 or 3 microsieverts an hour off them. Now, which place has higher levels of radiation than anywhere we've seen so far? The answer is an airplane. You know, as you gain altitude, there is less atmosphere above you to shield you from cosmic rays. So the level of radiation inside the plane can go up to 0.5 microsieverts per hour at 18,000 feet, up to 1 microsievert per hour at 23,000 feet, over 2 microsieverts per hour at 33,000 feet, and over 3 microsieverts per hour at even higher altitudes and towards the poles. That is Chernobyl nuclear reactor number 4. It melted down on April 26, 1986. So what happened was so much heat was generated inside that reactor that it basically blew the top off, spreading radioactive isotopes throughout this whole surrounding area and over into Europe. And that is why we can still detect the contamination here today. Now, right now it's reading around 5 microsieverts an hour. If I stayed here for 1 hour, my body would receive a similar dose to what you'd receive when you get a dental x-ray. So this is not a huge amount of radiation. And one of the reasons why the radiation level is too high is because they actually removed a couple meters worth of topsoil from this whole area. Then they dumped it somewhere. That's why we can stand here. We're driving into the Fukushima exclusion zone now. I'm just watching as the levels on my Geiger counter go up as we approach the zone. See those black bags at the side of the road? The Japanese are doing now exactly what the people in Chernobyl did, collecting up meters and meters of topsoil. The mask is probably overkill. It's just to stop radioactive dust from getting into my lungs. This is definitely one of the most radioactive places where I've been. Even though the release of radioactive material was less than Chernobyl, only about 10%. Because it's much fresher, only 3 years since the accident, much less of it has decayed. So I've been getting readings up around 5 to 10 microsieverts. Go into the hospital at Pripyat. And this is where the firemen were taken after they fought the fires at the Chernobyl reactor. And in the basement of this building, they have left all of the firemen's clothing. Once they realized it was so contaminated, they chucked it down there.
You can see there's a huge pile of that gear there.
Right outside the door, I'm getting 500 microsieverts an hour just outside the door. 1,500 microsieverts an hour. You know, if we stayed here for a couple hours, we'd receive an annual dose of background radiation.
That basement was the most radioactive place I visited, and it's one of the most radioactive places on Earth. If I'd stayed down there for 1 hour, I would have received 2,000 microsieverts. That's a year's worth of natural background radiation. Every yellow pixel here represents a banana. Now that might seem like a lot, but consider that in a CT scan, the patient receives about 7,000 microsieverts. That's 3 years worth of natural background radiation. It's been estimated that the people living around Fukushima will receive an additional 10,000 microsieverts over their lifetime due to the nuclear power disaster. For comparison, US radiation workers are limited to a maximum of 50,000 microsieverts per year. But that's less than another occupation, astronaut. An astronaut on the space station for 6 months will receive about 80,000 microsieverts worth of radiation. But not even they are exposed to the highest levels of ionizing radiation. So can you guess who is? The answer is a smoker's lungs. A smoker's lungs on average receive 160,000 microsieverts worth of radiation every year. That's due to the radioactive polonium and radioactive lead in the tobacco that they're smoking. So not only are they exposed to carcinogens and toxins, they also receive very high levels of radiation. So it's not the people of Fukushima or Chernobyl or radiation workers or even astronauts who receive the highest doses of ionizing radiation. That honor goes to your ordinary, average smoker.
Okay. So all you needed to know about radiation, and hopefully a public service announcement to not smoke ever. All right, so now that we know about radiation and the damage that it can do, how do we detect it? Because like I said before, it's invisible. So there's 3 main devices that we use to measure radiation. The one that you saw in the video was this number 2, the Geiger-Muller counter. But the first thing if you have like hospital staff or people that work in a lab, that are around radioactive materials, they use film badges. My first job out of university was working for a lab that made these little tiny radioactive seeds. They're basically like a little platinum, I think it was a platinum wire that was irradiated with some with, I don't remember which iodine isotope it was. He's coming in with 10 minutes. Okay. Yeah, so I worked in a lab, and the company made the, like I said, the radioactive seeds. They were about maybe a centimeter long, and those are used to treat cancer. So what the heck? So what they would do is the surgeon, if a tumor was not, if the tumor was not able to be removed, they could take these little radioactive seeds and like put it in the middle of the tumor, and the radiation would hopefully shrink the tumor. So I used to go into work every day, and I'd have to put on a film badge. And so that measures the amount of radiation you're exposed to. So make sure that everybody stays safe every day. And number two, the Geiger-Muller counter, usually we just call it a Geiger counter. That's what he was using in the video. Usually makes little ticking sounds based on how much radiation is nearby. And then number three is a scintillation counter. So this is an example of a film badge. There are many different uses, which I won't get to today, but many different uses for radiation that we do in both medicine and in agriculture. And so people that work around materials like that, they have to wear these film badges. Then we have the Geiger counter, and it counts electric pulses that are carried by gas in the air that's been ionized by the radiation. This one is used to detect beta particle, beta particles, and I think there's something behind that, probably alpha rays or beta, I don't know, something, gamma radiation. Okay, and this is going to explain how the Geiger counter works.
Say you've settled in for a day of gaming glory and you're busy cruising the radioactive wasteland of Fallout 4 when suddenly your speakers start emitting a crackling, clicking. Gamers aren't the only ones who recognize that sound. It's the characteristic noise of a Geiger counter detecting radiation. But it turns out that what you're really hearing is the sound of rogue electrons. The Geiger counter was developed in 1908 by Hans Geiger and perfected 20 years later by his student, Walter Mueller. So the radiation detector inside it is called, surprise, surprise, a Geiger-Muller or GM tube. The tube is made of metal, so it conducts electricity and is filled with a gas that's normally inert or non-reactive, like neon. A long metal rod runs through the middle with a power source charging it. Everything is stable because the inert gas between the rod and the walls doesn't conduct electricity. At least not yet. That's where radiation comes in. At the most basic level, radiation is how energy travels through space and is transferred between things. Geiger counters specifically measure ionizing radiation, radiation with enough energy to strip electrons from atoms, leaving behind positively charged ions. This also makes it powerful enough to damage DNA, which is why ionizing radiation is dangerous for living things, and why we have a vested interest in detecting it. When a radiation atom decays, it produces ionizing radiation in the form of subatomic particles, and with a Geiger counter, that's what you're looking to detect. When the ionizing radiation passes through the gas inside the GM tube, it knocks electrons off the gas atoms inside. The newly freed electrons are attracted to the positively charged rod at the center, so they zoom towards it. As they do, they knock electrons off of other atoms in what's called a Townsend avalanche. This cascade of atoms being ionized creates enough charged particles inside the tube to briefly conduct electricity between the rod and the walls, so there's a momentary surge of current. When the tube is connected to a speaker, the current causes a rapid jerking movement of the speaker components, which is that crackling or popping noise. While the electrons move toward the middle, the positive gas ions head the other way. When they hit the walls of the tube, they pick up an electron from the metal, returning to their original state and resetting the detector. The same crackling can also happen with any abrupt change in current running through your speakers, like if you accidentally roll your gaming chair over your audio cables. Thankfully, though, that type of crackling doesn't mean you need to go find a lead shield. Now, tweaks to the tube design and gas inside can make different Geiger counters slightly more or less sensitive to different kinds of ionizing radiation, but they're only really useful for detecting somewhat low levels of radiation. That's because any radiation that hits before the tube finishes resetting isn't detected, so they actually underestimate the danger in high radiation areas. So this probably goes without saying, but if you hear a Geiger counter crackling, stay away. Unless you've got some mutant hound chops or a refreshing beverage to flush your rads, that is. Thanks for watching this episode of SciShow, brought to you by our...
Okay, and then finally, we have the scintillation counters. The radiation can be detected when it transfers energy to a substance that scintillates or absorbs ionizing radiation and emits visible light. And you can see from the diagram on the bottom how that works. You've got radiation that basically turns into light, and then you've got a measuring device on the other side. So the scintillation counter is going to convert that scintillating light to an electrical signal to detect the radiation. Okay, I've got 5 minutes left, so I'm just going to stop there because